Good day. I, Joanna, together with my partner Abigail, we're going to discuss the Chapter 9 of the Principles of Electronic Communication Systems by Louis E. Frenzel. Chapter 9 is all about communication receivers. The topic covered in Chapter 9 are basic principles of signal reproduction, super heterodyne receivers, frequency conversion, intermediate frequency and images, noise, typical receiver circuits, receivers and transceivers. In radio communication systems, the transmitted signal is very weak when it reaches the receiver, particularly when it has traveled over a long distance. The signal, which has shared the free space transmission media with thousands of other radio signals, has also picked up noise of various kinds. Radio receivers must provide the sensitivity and selectivity that permit full recovery of the original intelligence signal. The radio receiver best suited to this task is known as the super heterodyne receiver. Invented in the early 1900s, the super heterodyne is used today in most electronic communication systems. This chapter reviews the basic principles of signal reception and discusses various super heterodyne circuits, including direct conversion. A communication receiver must be able to identify and select a desired signal from the thousands of others present in the frequency spectrum, which is called selectivity, and to provide sufficient amplification to recover the modulating signal, or the sensitivity. A receiver with good selectivity will isolate the desired signal and greatly attenuate another signals. A receiver with good sensitivity involves high circuit gain. Selectivity, Q, and bandwidth. Selectivity in a receiver is obtained by using tuned circuits and filters. LC-tuned circuits provide initial selectivity. Filters provide additional selectivity. By controlling the Q of a resonant circuit, you can set the desired selectivity. The optimum bandwidth is one that is wide enough to pass the signal and its sidebands but narrow enough to eliminate signals on adjacent frequencies. As you can see on the graph, the rate of attenuation or roll-off of an LC-tuned circuit is gradual. Adjacent signals will be attenuated, but in some cases, not enough to completely eliminate interference. Increasing the Q will further narrow the bandwidth and improve the steepness of attenuation, but narrowing the bandwidth in this way can be taken only so far. The next one is shape factor. The sides of a tuned circuit response curve are known as skirts. The steepness of the skirts, or the skirt selectivity, of a receiver is expressed as the shape factor, the ratio of the 60 decibel down bandwidth to the 6 decibel down bandwidth. The lower the shape factor, the steeper the skirts and the better the selectivity. A communication receiver's sensitivity, or ability to pick up weak signals, is mainly a function of overall gain, the factor by which an input signal is multiplied to produce the output signal. In general, the higher the gain of a receiver, the better its sensitivity. The greater gain that a receiver has, the smaller the input signal necessary to produce a desired level of output. High gain in communication receivers is obtained by using multiple amplification stages. Another factor that affects the sensitivity of a receiver is the signal-to-noise ratio. Noise is the small random voltage variations from external sources and from noise variations generated within the receiver circuits. This noise can sometimes be so high, many microvolts, that it masks or obliterates the desired signals. One method of expressing the sensitivity of a receiver is to establish the minimum discernible signal, the MDS, in the input signal level that is approximately equal to the average internally generated noise value. This noise value is called the noise floor of the receiver. MDS is the amount of signal that would produce the same audio power output as the noise floor signal. The MDS is usually expressed in decibel. Another often used measure of receiver sensitivity is microvolts or decibels above 1 millivolts and decibels above 1 microwatts. The simplest radio receiver is a crystal set consisting of a tuned circuit, a diode detector, and earphones. The tuned circuit provides the selectivity. The diode and a capacitor serve as an AM demodulator. The earphones reproduce the recovered audio signal. The next one is tuned radio frequency receiver. In the tuned radio frequency receiver, sensitivity is improved by adding a number of stages to RF amplification between the antenna and detector, followed by stages of audio amplification. The RF amplifier stages increase the gain before it is amplified to the detector. The recovered signal is amplified further by audio amplifiers, which provide sufficient gain to operate a loudspeaker. This is a sample illustration of crystal set. Many RF amplifiers use multiple tuned circuits. Whenever resonant LC circuits tuned to the same frequency are cascaded, overall selectivity is improved. The greater the number of tuned stages cascaded, the narrower the bandwidth and the steeper the skirts. The main problem with TRF receivers is tracking the tuned circuits. In a receiver, the tuned circuits must be made variable so that they can be set to the frequency of the desired signal. Another problem with the TRF receivers is that selectivity varies with frequency. So what is super heterodyne receivers? Super heterodyne receivers convert all incoming signals to a lower frequency, known as the intermediate frequency, at which a single set of amplifiers and filters is used to provide fixed level of sensitivity and selectivity. Most of the gain and selectivity in a super heterodyne receiver are obtained in the IF amplifiers. The key circuit is the mixer, which acts as a simple amplitude modulator to produce sum and difference frequencies. The incoming signal is mixed with a local oscillator signal to produce this conversion. The figure shows a general block diagram of a super heterodyne receiver. In the following sections, the basic function of each circuit is examined. Although individual circuits are discussed in the following sections, keep in mind that today most receivers are made up of circuits fully integrated on a signal chip of silicon or other semiconductor material. Such circuits cannot usually be changed or accessed. The next one is RF amplifier. The antenna picks up the weak radio signal and feeds it to the RF amplifier, also called a low noise amplifier. RF amplifiers provide some initial gain and selectivity and are sometimes called press selectors. Tuned circuits help select the frequency range in which the signal resides. The tuned circuits in fixed tune receivers can be given a very high Q, so that excellent selectivity can be obtained. The tuned circuits must resonate over a wide frequency range. Therefore, the Q, bandwidth, and selectivity of the amplifier change with the frequency. In communication receivers that do not use an RF amplifier, the antenna is connected directly to a tuned circuit at the input to the mixer, which provides the desired initial selectivity. This configuration is practical in low-frequency applications where extra gain is simply not needed. RF amplifiers improve sensitivity because of the extra gain, improve selectivity because of the added tuned circuits, and improve the S/N ratio. RF amplifiers minimize oscillator radiation. The local oscillator signal is relatively strong, and some of it can leak through and appear at the input to the mixer. If the mixer input is connected directly to the antenna, some of the local oscillator signal radiates, possibly causing interference to other nearby receivers. The RF amplifier between the mixer and the antenna isolates the two, significantly reducing any local oscillator radiation. Both bipolar and the field effect transistors, made with silicon, GaAs or SiGe, can be used as RF amplifiers. The selection is made based upon frequency, cost, integrated versus discrete, and desired noise performance. The next one are mixers and local oscillators. The output of the RF amplifier is applied to the input of the mixer. The mixer also receives an input from a local oscillator or frequency synthesizer. The mixer output is the input signal, the local oscillator signal, the sum and difference frequencies of these signals. A tuned circuit at the output of the mixer selects the difference frequency, or intermediate frequency. The sum frequency may also be selected as the IF in some applications. The mixer may be a diode, a balanced modulator, or a transistor. MOSFETs and hot carrier diodes are preferred as mixers because of their low noise characteristics. The local oscillator is made tunable so that its frequency can be adjusted over a relatively wide range. As the local oscillator frequency is changed, the mixer translates a wide range of input frequencies to the fixed IF. The next one is IF amplifier. The output of the mixer is an IF signal containing the same modulation that appeared on the input RF signal. The signal is amplified by one or more IF amplifier stages, and most of the gain is obtained in these stages. Selective tuned circuits provide fixed selectivity. Since the intermediate frequency is usually lower than the input frequency, IF amplifiers are easier to design and good selectivity is easier to obtain. If amplifiers are easier to design and good selectivity is easier to obtain, crystal, ceramic, or SAW filters are used in most IF sections to obtain good selectivity. Some forms of receivers use DSP filters for selectivity. Demodulators. The highly amplified IF signal is finally applied to the demodulator, which recovers the original modulating information. The demodulator may be a diode detector for AM, a quadrature detector for FM, or a product detector for SSB. The output of the demodulator is then usually fed to an audio amplifier. In modern digital superheterodyne radios, the IF signal is the first digitized by an analog to digital converter, or ADC, and then sent to a digital signal processor, DSP, where the demodulator is carried out by a programmed algorithm. The recovered signal in digital form is then converted back to analog by a digital to analog converter, or DAC. Automatic gain control. The output of a demodulator is usually the original modulating signal, the amplitude of which is directly proportional to the amplitude of the received signal. The recovered signal, which is usually AC, is rectified and filtered into a DC voltage by a circuit known as the automatic gain control circuit. This DC voltage is fed back to the IF amplifiers and sometimes the RF amplifier to control receiver gain. AGC circuits help maintain a constant output level over a wide range of RF output signal levels. The amplitude of the RF signal at the antenna of a receiver can range from a fraction of a microvolt to thousands of microvolts. This wide signal range is known as the dynamic range. Typically, receivers are designed with very high gain so that weak signals can be reliably received. However, applying a very high amplitude signal to a receiver causes the circuits to be overdriven, producing distortion and reducing intelligibility. With AGC, The overall gain of the receiver is automatically adjusted depending on the input signal level. The signal amplitude at the output of the detector is proportional to the amplitude of the input signal. If it is very high, the AGC circuit produces a high DC output voltage, thereby reducing the gain of the IF amplifiers. This reduction in gain eliminates the distortion normally produced by a high voltage input signal. When the incoming signal is weak, the detector output is low. The output of the AGC is then a smaller DC voltage. This causes the gain of the IF amplifiers to remain high, providing maximum applications. Now, we are going to define frequency conversion. Frequency conversion is the process of translating a modulated signal to a higher or lower frequency, while retaining all the originally transmitted information. In radio receivers, high-frequency signals are converted to a lower intermediate frequency. This is called down conversion. In satellite communications, the original signal is generated at a lower frequency and then converted to a higher frequency. This is now what we call up conversion. Then mixing principles. Frequency conversion is a form of amplitude modulation carried out by a mixer circuit or converter. The function performed by the mixer is called heterodyning. Mixers accept two inputs. The signal to be translated to the another frequency is applied to one input, and the sine wave from a local oscillator is applied to the other input. The signal to be translated can be a simple sine wave or any complex modulated signal containing sidebands. The local oscillator signal usually appears in the mixer output, as does the original input signal in some types of mixer circuits. These are not needed in the output and are therefore filtered out. Either the sum or difference frequency in the output is desired signal. To translate the input signal to a lower frequency, the lower sideband or difference signal is chosen. The local oscillator frequency will be chosen such that when the information signal is subtracted from it, a signal with the desired lower frequency is obtained. When translating to a higher frequency, the upper sideband or sum signal is chosen. Again, the local oscillator frequency determines what the new higher frequency will be. A tuned circuit or filter is used at the output of the mixer to select the desired signal and reject all the others. Here is the schematic diagram of a mixer circuit. Another type of mixer and converter circuits is the diode mixer. The primary characteristic of mixer circuits is nonlinearity. Any device or circuit whose output does not vary linearly with the input can be used as a mixer. One of the most widely used types of mixer is the simple diode modulator. Diode mixers are the most common type found in microwave applications. The input signal is applied to the primary winding of the transformer. The signal is coupled to the secondary winding and applied to the diode mixer, and the local oscillator signal is coupled to the diode by the way of a capacitor. The input and local oscillator signals are linearly added and applied to the diode, which produces the sum and difference frequencies. The output signals are developed across the tuned circuit, which selects the difference frequency. This is the schematic diagram of a simple diode mixer. There are two types of balanced mixer, the singly balanced mixer and the doubly balanced mixer. The singly balanced mixer is a popular mixer circuit using two diodes, while doubly balanced mixer, this version of diode balance modulator, is probably the single best mixer available, especially to very high frequency, ultra high frequency, and microwave frequencies. Balanced modulators are also widely used as mixers. These circuits eliminate the carrier from the output, making the job of filtering much easier. Any of the balanced modulator described previously can be used in mixing applications. While the fat mixers. Fats makes good mixers because they provide gain, have low noise, and offer a nearly perfect square law response. One of the best reasons for using a FET mixer is that its characteristic drain current versus gate voltage curve is a perfect square law function. FETs are the preferred mixer in most receivers. Then, the NE602, a typical IC mixer, is also known as a Gilbert transconductance cell or Gilbert cell. It consists of a double balanced mixer circuit made up of two cross-connected differential amplifiers. The NE602 uses bipolar transistors. An image reject mixer is a special type of mixer used in designs in which images cannot be tolerated. It uses Gilbert cell mixers in a configuration like that used in a phasing type SSB generator. The circuits show the details of the mixer itself. The first one is the block diagram and the pinout, and the second one is the simplified schematic. Bipolar transistors Q1 and Q2 form a differential amplifier, with current source Q3 and Q4 and Q5 form another differential amplifier with current source Q6. Note that the inputs are connected in parallel. The collectors are cross-connected. For example, the collector of Q1 is connected to the collector of Q4 instead of Q3, as would be the case for a parallel connection, and the collector of Q2 is connected to the collector of Q3. This connection results in a circuit that is like a balanced modulator, in that internal oscillator signal and the input signal are suppressed, leaving only the sum and difference signals in the output. The output may be balanced or single-ended, as required. A filter or tuned circuit must be connected to the output to select the desired sum or difference signal. Local oscillator and frequency synthesizers. The local oscillator signal for the mixer comes from either a conventional LC-tuned oscillator or a frequency synthesizer. The simpler continuously tuned receivers use an LC oscillator. Channelized receivers use frequency synthesizers. A local oscillator is sometimes referred to as a variable frequency oscillator or VFO. An amplifier, for example FET, is connected as a Colpitts oscillator. Feedback is developed by a voltage divider made up of capacitors. The frequency is set by a parallel tuned circuit. The output is taken across an RFC and is buffered by a direct coupled emitter follower. Most drift comes from the LC circuit components themselves. Even inductors, which are relatively stable, have slight positive temperature coefficients, and the special capacitors to change little with temperature are essential. Usually, negative temperature coefficient ceramic capacitors are selected to offset the positive temperature coefficient of the inductor. Capacitors have a mica dielectric are also used. A diagram of VFO for receiver local oscillator service. C3 can be replaced by a Varacto reversed bias to make it act as a capacitor. Then a potentiometer applies a variable DC bias to change the capacitance and thus the frequency. The next one is the frequency synthesizer. Most new receiver designs incorporate frequency synthesizers for the local oscillator, which provides some important benefits over simple VFO designs. The synthesizer is usually of the phase-locked loop design, and the output is locked to a crystal oscillator reference, which provides high stability. Tuning is accomplished by changing the frequency division factor in the PLL, resulting in incremental rather than continuous frequency changes. The former disadvantages of frequency synthesizers, higher cost and greater circuit complexity, have been offset by the availability of low-cost PLL synthesizer ICs, which make local oscillator design simple and cheap. Most modern receivers, from AM or FM car radios, stereos, and TV sets to military receivers and commercial transceivers, use frequency synthesis. As stated previously, one of the disadvantages of very high-frequency PLL synthesizers is that the VFO output frequency is often higher in frequency than the upper operating limit of the variable modulus frequency divider ICs commonly available. One approach to its problem is to use a prescaler to reduce the VFO frequency before it is applied to the variable frequency divider. Another is to reduce the VFO output frequency to a lower value within the range of the dividers by down-converting it with the mixer, as illustrated in the figure. The VFO output is mixed with a signal from another crystal oscillator, and the output is mixed with a signal from another crystal oscillator, and the difference frequency is selected. With some UHF and microwave receivers, it is necessary to generate the local oscillator signal at a lower frequency and then use a PLL frequency multiplier to increase the frequency to the desired higher level. The position of this optional multiplier is shown by the dotted line in the figure. The primary objective in the design of an IF stage is to obtain good selectivity. Narrow band selectivity is best obtained at lower frequencies. At low frequencies, circuits are more stable with high gain. At low frequencies, image interference is possible. An image is an RF signal 2 times the IF below or above the incoming frequency. At higher frequencies, circuit layouts must take into account stray inductances and capacitances. At higher frequencies, there is a need for shielding. With very high circuit gain, some of the signal can be fed back in phase and cause oscillation. Oscillation is not as much of a problem at lower frequencies. However, when low IFs are selected, a different sort of problem is faced, particularly if the signal to be received is very high in frequency. This is the problem of images. An image is a potentially interfering RF signal that is spaced from the desired incoming signal by a frequency that is 2 times the intermediate frequency above or below the incoming frequency. This figure shows the relationship between the image frequencies and the signal, while the next figure shows the relationships between the signal, local oscillator, and image frequencies. The mixer produces the difference between the local oscillator frequency and the desired signal frequency, or the difference between the local oscillator frequency and the image frequency. In both cases, the IF is 10 MHz. This means that a signal spaced from the desired signal by 2 times the IF can also be picked up by the receiver and converter to the IF. When this occurs, the image signal interference with the desired signal.
Next, we have solving the image problem. High-Q-tuned circuits should be used ahead of the mixer or RF amplifier to reduce image interference. Since image interference occurs only when the image signal is allowed to appear at the mixer input, this image can also be rejected if the selectivity of the RF amplifier and tuned circuit is good enough. However, in such cases, selectivity becomes a problem. This is when receivers have broadband RF amplifiers that allowed many frequencies within a specific band to pass, and other receivers must be made tunable over a wide frequency range. So the IF is made as high as possible for effective elimination of the image problem. Yet, it is low enough to prevent design problems. In most receivers, the IF varies in proportion to the frequencies that must be covered. So next is this figure. So this figure shows signal frequency with low Q-tune circuits compared with a low IF that causes images to pass and interfere. So as we can see, the red one is the one with low Q-tune circuits, while the green one is the low IF. So next we have the dual conversion receivers. Another way to obtain selectivity while eliminating the image problem is to use a dual conversion super heterodyne receiver. So in the next slide, we have a dual conversion super heterodyne receiver. This is its figure. As we can see, the receiver uses two mixers and a local oscillators. So that is a typical receiver. So this figure shows how the different frequencies are obtained. As we can see, the first mixer. This first mixer converts the incoming signal to a high intermediate frequency to eliminate the image, while the second mixer converts that IF down to a much lower frequency where good selectivity is easier to obtain. Each of these mixers produces different frequencies. So the first LO is the one that provides the tuning for the receiver, while the second is the one fixed in frequency. Since this dual conversion heterodyne needs to convert only one fixed IF to a lower IF, this local oscillator does not have to be tunable. Well, in some receivers, the second LO is the one that provides for the tuning, and the first LO is the one with with fixed frequency. A special version of the super heterodyne is known as the direct conversion or the DC or zero IF receiver or the ZIF receiver. So instead of translating the incoming signal to another intermediate frequency, this DC receiver is the one responsible in converting the incoming signal directly to baseband. Or, in other words, they are the one that performs the modulation of the signal as part of the translation. So, the low noise amplifier or the LNA boosts the signals before the mixer, and it is also said here that the local oscillator or the LO frequency is set to the frequency of the incoming signal. So the baseband output is passed via a low pass filter or a LPF. This figure shows the basic ZIF receiver architecture, or it is a direct conversion receiver. So first we have the LNA. This LNA boosts the signal level before the mixer. The LO frequency, as we can see, this LO frequency is set to the frequency of the incoming signal, while the mixer here is acting as the modulator. The next is the LPF or the low pass filter. This is the one that removes the sum, which is twice the LO frequency. Then we have the modulated baseband output. So we have the direct conversion receivers, advantages and disadvantages. First advantage of this DC receiver is that it has no separate IF filter needed. This is usually a crystal, ceramic, or SAW filter that is expensive and takes up valuable PCB space in compact design. Second, no separate detector circuit is needed because the modulation is inherent in the technique. The third one is in transceivers that use half duplex and in which the transmitter and receiver are on the same frequency, only one PLL frequency synthesizer voltage controlled oscillator is needed. And last is there is no image problem. So with all these benefits results in simplicity and its attendant lower cost. While the disadvantages of dead DC receivers are in designs with no RF amplifier or the LNA, the LO signal can leak through the mixer to the antenna and radiate. A LNA reduces this likelihood. Careful design is required to minimize this radiation. Second is an undesired DC offset can develop in the output. And last is that ZIF receiver can be used only with the CW, AM, SSB, or DSB. It cannot recognize phase or frequency variation. We have here another figure. This shows a direct conversion receiver that is typical of those that uses digital modulation. So first, the incoming signal from the antenna is sent to a SAW filter. So this SAW filter provides some initial selectivity. While next is the LNA that provides the amplification. So this LNA or the LNA, the output of this LNA is fed to two mixers. The local oscillator signal, usually from a synthesizer, is fed directly to the upper mixer, the sine theta, and to a 90-degree phase shifter that supplies the lower mixer, the cosine theta. As we can remember, the LO frequency is equal to the incoming signal frequency. These two mixers provide baseband signals at their outputs. The double LO frequency signals resulting from mixing are removed with a low-pass filter, this 2LPF. The two baseband signals are separated in phase by 90 degrees. The upper signal is usually referred to as the in-phase, that with letter I, signal, while the lower signal is this, which referred to as quadrature signal or the Q. The I and Q signals are then sent to analog to digital converters, these two ADCs, where they are converted to binary signal. The binary signals are then sent to a digital signal processors or the DSP. This DSP contains a pre-stored subroutine that performs the demodulation. So the output from the demodulation subroutine is fed to an external digital to analog converter or the DAC, where the original modulating signal is produced. This I to Q direct conversion architecture is now one of the most common receiver architectures used in cell phones and wireless networking ICs. Next, we have the software-defined radio or the SDR. It is a receiver in which most of the functions are performed by a digital signal processor or the DSP. The benefits of these SDRs are improved performance and flexibility. The receiver characteristics, which involves the type of modulation, selectivity, and etc., can be easily changed by running a different program. Our next topic is about noise. Noise is said to be an electronic signal that gets added to a radio or information signal as it is transmitted from one place to another. So this noise is not the same as interference from other information signals. If the noise level is high enough and or the signal is very weak, the noise can completely obliterate the original signal. Obliterate meaning to destroy completely so that nothing is left. The noise level in a system is proportional to the temperature and bandwidth, the amount of current flowing in a component, the gain of the circuit, and the resistance of the circuit. So increasing any of this will also increase the noise. Therefore, to obtain low noise, we should use low gain circuits. So when the transmission is over short distances or high power transmitters are being used, noise will be a problem. Next is the signal to noise ratio. The signal to noise ratio indicates the relative strength of the signal and the noise in a communication system. The stronger the signal and the weaker the noise, the higher the SN ratio. So this SN ratio is a power ratio. If the SN ratio is less than 1, the dB value or the decibel value will be negative and the noise will be stronger than the signal. Under noise, we have external noise and internal noise. First is external noise. These are noise, this is the noise that comes from sources over which we have little or no control, such as industrial sources, atmospheric sources, and space. Under industrial sources, we have motors, generators, and manufactured equipment. Well, in atmospheric sources, we have this atmospheric noise, also called static. And in space, the sun radiates a wide range of signals in a broad noise spectrum. Next is internal noise. Electronic components in a receiver such as resistors, diodes, and transistors are major sources of internal noise. Internal noise, although it is low level, is often great enough to interfere with weak signals. The main source of this in a receiver are thermal noise, semiconductor noise, and the intermodulation distortion. Expressing noise levels. The noise quality of a receiver can be expressed in the following terms. First, noise factor. This is the ratio of the Sn power at the input to the Sn power at the output. The noise figure. This is when the noise factor is expressed in decibels. Noise temperature. Most of the noise produced in a device is thermal, which is directly proportional to the temperature, and this term noise temperature is used. The SINAD, it is the composite signal. The SI means the signal, plus N is the noise, A in the end, and D is the distortion. So signal, noise, and distortion divided by noise and distortion contributed by the receiver. Noise in cascaded stages. Noise has its greatest effect at the input to a receiver because that is the point at which the signal level is lowest. The noise performance of a receiver is determined in the first stage of the receiver, usually an RF amplifier or mixer. So, the design of cascaded circuits must ensure the use of very low noise components, and we should take into consideration the current, the resistance, bandwidth, and gain figures in these circuits. Noise is no longer a problem beyond the first and second stages of the cascaded circuit. Next, we have typical receiver circuits. This includes RF amplifiers, the IF amplifiers, AGC, AFC, and special circuits. So first we have the RF input amplifier, or also called as low noise amplifier, or the LNA. This processes the very weak input signals, increasing their amplitude prior to mixing. So low noise components here are used to ensure a sufficiently high SN ratio. The selectivity here should be such that it effectively eliminates images. And this RF amplifier is typically a Class A circuit that can be configured with bipolar or field effect transistors. So in the next slide we have this image, a typical RF amplifier used in receiver front ends. So this FET circuit is particularly effective because of their high input impedance, which minimizes loading in tuned circuits. And most FET circuits also have a lower noise figure, that's why it is said to be effective. Next is the IF amplifier. Most of the gain and selectivity in a super heterodyne receiver are obtained in this kind of amplifier. So IF amplifier are also tuned Class A circuits capable of providing gain in the 10 to 30 decibel range. Usually, two or more IF amplifiers are used to provide adequate receiver gain. Ferrite core transformers are used for coupling between stages, and selectivity here is provided by tuned circuits. We also have the traditional IF amplifier circuits, or the coupled circuit selectivity. So this is the changing the amount of coupling between the primary and secondary windings, allowing the desired amount of bandwidth to be obtained. At some particular degree of coupling known as the critical coupling, the output reaches a peak value. In FM receivers, one or more of the IF amplifier stages is used as a limiter to remove any amplitude variations of the FM signal before the signal is applied to the demodulator. And lastly, most modern receivers do not use LC tunes filters, but instead use crystal, ceramic, mechanical, SAW, or the DSP filters. The next typical receiver circuit is the AGC, or the automatic gain control circuits. The receiver gain is typically far greater than required for adequate reception. Excessive gain usually causes the received signal to be distorted and the transmitted information to be less intelligible. So these AGC circuits are more effective in handling large signals and give the receiver a very wide dynamic range. The gain of a bipolar transistor amplifier is proportional to the amount of collector current flowing. So there are two methods of applying the AGC. First is the reverse AGC and next is the forward AGC. So in the reversed AGC, it is proportional. The gain is proportional to the collector current. As the gain decreases, the collector current decreases also. While in the forward AGC is indirect. The gain can be reduced by increasing the collector current. So a stronger signal increases AGC voltage and base current and in turn increases collector current, reducing the gain is the forward AGC. Next is squelch circuit or also called as muting circuit. It is found in most communication receivers and it is also used to keep the receiver audio turned off until an RF signal appears at the receiver input. While in AM systems such as CB radios, the noise level is high and can be very annoying. So swell circuits provide a means of keeping the audio amplifier turned off during the time that noise is received in the background and enabling it when an RF signal appears at the input. So we have the SSB and the continuous wave reception. Communication receiver is designed for receiving SSB or the continuous wave reception signals have a built-in oscillator that permits recovery of the transmitted information. So a circuit called the bit frequency oscillator or the BFO is usually designed to operate near the IF. This BFO signal is applied to the demodulator along with the IF signal containing the modulation. So the term bit in the bit frequency oscillator refers to as the difference frequency output. This figure shows the use of a BFO. First, the BFO signal from the IF is injected directly to the balance modulator as shown, and however, the dots and dashes appears as an audio tone or the audio, which is the output, is heard mostly in speakers and earphones. The last typical receiver circuits is the IC or the integrated circuits. So a complete receiver usually consists of 3 or 4 ICs plus the coils, transformers, capacitors, and filters, while most modern receivers now are only contained on a single IC. So IC receivers are typically broken down into 3 major sections. First, the tuner with RF amplifier, mixer, and local oscillator. The IF section with amplifiers, demodulator, and AGC and muting circuits. And last is the audio power amplifier. So the second and third sections are entirely implemented with ICs. The tuner may or may not be. Far often the LNA is separate. We will now proceed to the last, the receivers and transceivers. A typical VHF receiver is designed to receive two-way aircraft communication between planes and airport controllers, which take place in the VFH range of about 118 to 135 MHz. Amplitude modulation is used in these receivers. These VHF receivers are designed to use a combination of discrete components and ICs. So in the next slide, this figure shows the typical VHF receiver. The single IC FM receiver. The Motorola MC3363 FM receiver IC chip contains all receiver circuits except for the audio amplifier, which is a separate chip. This is designed to operate at frequencies of about or up to about 200 MHz. It is also widely used in cordless telephones, paging receivers, and other portable applications. This dual conversion receiver or DC receiver contains 2 mixers, 2 local oscillators, a limiter, a quadrature detector, and squelch circuits. The first local oscillator has a built-in varactor that allows it to be controlled by an external frequency synthesizer. The last is the transceiver. Most Two-way radio communication equipment is packed so that both transmitter and receiver are in a unit, also known as transceiver. These transceivers range from large, high-power desktop units to small, packet-sized handheld units. So cell phones or transceivers are as well as the wireless local area networking units on PCs. Transceivers provides many advantages, such as the transmitters and receivers can share circuits, thereby achieving cost saving and smaller size. And also most transceivers now in our modern time uses a single silicon chip. In this slide, this figure is a general block diagram of a high-frequency receiver capable of CW and SSB operation. So, in transmission mode, the crystal filter provides sideband selection after the balance modulator. The filter provides selectivity for the IF section of the receiver. Tuned circuits may be shared. It can also tune input for the receiver and tune output for the transmitter. In most newer circuit designs, both the transmitter and receiver share a frequency synthesizer. And that's all for today. Thank you.